Okay, I think we can start.
Okay, then. So Lorenzo is a fourth year student on the computer science department, and I think Juan already introduced ComputeDRAM quite nicely.
Sorry,
So,
that was second year, not fourth.
Fourth? Oh, sorry.
Fourth semester.
Oh, fourth semester. Sorry about that. Fourth semester in computer science. Eventually, fourth year. So Lorenzo, please feel free to start.
All right. Hello, everyone. So I'll be talking about ComputeDRAM, in-memory compute using off-the-shelf DRAMs. And this paper was published in Micro in 2019. First, let's get a quick overview over the paper. There is a major performance and power consumption bottleneck in current computing systems, specifically the interconnect between main memory and the CPU. So we would like to alleviate this issue by performing computations in memory. The paper proposes purposefully violating DRAM timing constraints to achieve this. It further tested feasibility and reliability by evaluating 32 different modules from 7 different vendors. Any module that was able to reliably perform the operations was further tested for performance of 8-bit and OR and 8-bit addition. The results show that nearly all chips were able to perform row copy on at least some rows. 3 modules were further able to perform and OR operations. The testing showed that the reliability of the operations were high. Now let's cover some background information. Current computing systems are typically structured with a clear separation between the CPU and the main system memory, connected by a memory bus. This, however, has a few problems, as this memory bus is high in power usage, has limited bandwidth, and incurs a high latency cost. This problem has been known for well over 2 decades now and is canonically called the memory wall. As such, we would like to eliminate any unnecessary data movement across this bus. One way of achieving this is by moving the computation to main memory. In that case, the data doesn't need to be moved from system to memory, from the system memory to the CPU for computation and back again. This would lower power usage, leave the data bandwidth available for other data, and let the CPU work on different tasks. Now let's look at how current DRAM is structured. A DRAM chip consists of multiple banks, which are further subdivided into subarrays. The subarrays contain the actual memory and are organized into rows or word lines and columns or bit lines. At each intersection between a row and column, there is a single DRAM cell, which acts as a 1-bit storage cell. Typically, DRAM has around 512 rows and around 8 kilobytes of columns. The bit lines are connected to a single sense amplifier for each line, acting as a local row buffer. The local row buffer is then connected to the I/O bus. Now, a DRAM cell consists of a capacitor connected to the bit line via a transistor. If the word line is low, the capacitor is disconnected and the charge represents the current state of the cell. To read out the data from a cell, the bit line first has to be pre-charged with half of the supply voltage. After the word line is activated, charge sharing between the bit line and the capacitor will take place, slightly nudging the voltage on the bit line towards the original state of the capacitor. Afterwards, the sense amplifier will activate, pulling the bit line either towards the supply voltage or 0, depending on the voltage on the bit line. The charge in the capacitor is now refreshed, and the data is stored in the row buffer, ready to be written or read or written to. Now, the memory controller needs some way of communicating with the DRAM, and this is done through DRAM commands. And there are 3 major commands to take note. First, to copy the data from one row into the row buffer, the memory controller will issue the activate command. This will first open the selected row, and then afterwards, after enough time has passed for the charge to equalize over the bit line, activate the sense amplifiers and refresh the data. The data can now be read or written by issuing a read or write command, which will then copy one cache line of data from or to the memory. After all operations on the row have been completed, a pre-charge command must be issued to prepare the memory for the next activate. This will first close any opened rows, and then after that is complete, drive the bit lines back to half of the supply voltage, making the chip ready for the next operation. For the purpose of this paper, we only need to concern ourselves with the activate and pre-charge commands. Since the commands require some time to execute, timing constraints that specify the minimum delay between 2 instructions must be followed. The 2 constraints we need to take a look at are first, the row access strobe, which determines the minimum delay between an activate and the next pre-charge, and the row pre-charge time, which is the minimum delay between a pre-charge and the next activate. The first paper to abuse DRAM structure to perform in-memory operation was row clone. Row clone proposed performing high bandwidth copy inside the subarray by first opening up the source row and letting the sense amplifier copy the data into the row buffer as normal. And afterwards, instead of closing and resetting the line, if a second row was opened, the drive strength of the row buffer would then copy the data into the destination row as well. This was a pioneering work and spawned many follow-up papers, one of which was Ambit, which extended the mechanism to support in-memory and OR operations. The key idea here is to open up 3 rows at the same time before activating the sense amplifiers. In this case, the charge sharing would pull the bit line towards the majority state of the cells, which would then be amplified by the sense amplifier. To illustrate this, let's assume in a situation with a majority high configuration. After all 3 rows are open, charge sharing will pull the bit line slightly above VDD/2, which will then turn into a high after the activation of the sense amplifiers. Similarly, in a majority low state, the bit line will end up slightly below VDD/2 after opening of the 3 rows, which will end up a logical 0 after activation of the sense amplifiers. To perform logical AND with this, we can open up a constant 0 row in addition to the 2 operands. In this case, a majority high is only possible if both of the operands are high, which is then equivalent to a logical AND. Similarly, for logical OR, this can be done by opening up a constant 1 row in addition to the 2 operands. Now, any of the operands being high will end up in a majority high, which is obviously equivalent to logical OR. While both of these papers have demonstrated a mechanism that uses the existing DRAM structures, they still require some changes. Both proposed adding custom logic to the row decoder, and Ambit further proposed adding additional connectors to the sense amplifiers to perform negation. DRAM manufacturing, however, is a highly optimized low-margin business, so any logic or change could potentially incur high costs. With all the background information out of the way, let's get to the actual paper. ComputeDRAM sets out to test if it is possible to perform these operations without any modifications to existing DRAM, as well as constructing a framework that will allow us to perform arbitrary computations using the available operations. What? Oh, God. Well, that's a bit unfortunate. Very unfortunate indeed. All right, let's go. Let's get back on track then. So the key idea of the paper is that we can purposefully violate the DRAM timing constraints to achieve non-standard state. For example, if we reduce the time between sending a pre-charge and an activate command, thereby violating the row access trope, we can interrupt stages of the activate command before they are executed. We will first start with row copy, since this is the easiest operation to understand. We first open up the source row and let the sense amplifiers activate as usual. Now, ideally, we would like to immediately issue another activate command to open up the destination row. However, as the researchers have discovered, the DRAM chips will ignore the second activate unless a pre-charge is issued in between. So we have to send a pre-charge first. Now, however, we have to prevent the bit lines from being driven to VDD/2, which would erase our data. To achieve this, we will send the next activate prematurely, violating the row pre-charge time and interrupting the pre-charge command. The activate will also open up the destination row, copying the data that is still present on the bit line into it, and then let the sense amplifiers refresh it. The row copy is now complete. Now, the question is, can we extend this to perform AND or OR operations? And sadly, there are some problems with that. First, for AND and OR, we need all rows to be opened before the sense amplifiers activate. In the case of row copy, we let the activate play out as usual, including activation of the sense amplifiers in the first activate. So to interrupt the activate, however, we can use the same mechanism we previously applied to the pre-charge command. Violate the row access strobe and interrupt the activation of the sense amplifiers. Another issue is that we want to open up 3 rows at once. Again, though, there is a neat mechanism that we can use to achieve this. In this case, we will abuse the fact that the address won't change instantaneously when we switch rows. So the idea is that if we are fast enough, we can force a row to be opened while the address is still in the process of transitioning. The authors have tested this and determined that the address is likely updated in order of least significant bit to most significant bit. So for example, if we assume that we start out with row 1 and transition to row 2, then the first bit that will be the first bit will be updated, which is the least significant bit here. Then the second least significant bit, and so on. In this case, there is one intermediary row which will be opened. This can also be seen in the table here. From here on out, we will have R1. We will always have R1 determine the first row that is opened, R2 the second row that is opened, and R3 being the implicitly opened row. There is one last problem to tackle. Ideally, we would expect the majority state to be the result after charge sharing. However, reality is a bit more complex. The issue here is that we don't actually open up all the rows at the same time, but sequentially. This means that some rows will have different amount of time to affect the bit line, which potentially alters the result. The authors have tested all different combinations of state and determined these results. The X here indicates unpredictable results. We can see there are some combinations, though, that do suit our needs. For once, we can use R1 and R2 for the operands and a constant 1 in R3 to perform the OR operations. Similarly, we can use R3 and R2 for the operands and a constant 0 in row 1 to perform AND operations. With all that out of the way, we can now finally look at how logical AND is implemented in practice. As discussed on the last slide, we will place the two operands in R2 and R3, while R1 contains a constant 0. We start out by sending the first activate as usual. We then violate the row access trope to interrupt the activation of the sense amplifier by sending the pre-charge command immediately. This time, we also want to prevent the closing of the rows, so without any delay, we immediately send the next activate command. The tight timings will cause a third row to be opened up implicitly during address transition. We then let the last activate finish execution, enabling the sense amplifiers and completing the execution of the AND. Logical OR is performed in exactly the same manner, just with different placement of operands and a constant 1 instead of a 0. As mentioned previously, we place the two operands in row 1 and row 2 while having the constant 1 in row 3. We first open up row 1, followed by a pre-charge, which again is immediately followed by the next activate, implicitly opening up row 3 and interrupting the pre-charge. We let the last activate play out and finish with the result stored in all 3 opened rows. As is usually the case, there are some problems that arise when we try to implement this in the real world. Firstly, sometimes some rows just aren't capable of performing the operations. This can be for a variety of reasons. For one, the manufacturing process isn't perfect and different cells can have different capacitances. In that case, it is possible that we get a combination of capacitances where one is significantly stronger or weaker than the others, which means the result of charge sharing might not be the majority state. It is also possible to get cells that are faulty, and manufacturers typically don't like to throw out entire chips just because there are a few faulty rows. So in order to deal with this, they add additional rows to subarrays that can be remapped to the faulty rows. While this is great for the manufacturers and for your wallet, it does pose a few problems for us, as the row now no longer has the address that we expect it to have, making it impossible to use it when we are trying to open up 3 rows. Lastly, DRAM cells will also deteriorate over time, meaning that rows that once were able to perform an operation might not be in the future. To combat all of these issues, the paper proposes to detect these bad rows at startup and exclude them from computations. Another question that still remains is if we can actually use these operations to perform whatever we want. And the answer is sadly no. We only have AND and OR available, which is not enough to compute all formulas in Boolean algebra. We need negation for functional completeness. There is, however, a way to make this work without adding any negation logic to the DRAM. Namely, it is possible to transform any formula with negation in any term in such a way that the only negated terms are the input variables themselves. Now, if you don't believe me that that is the case, you can have a look at conjunctive normal form and disjunctive normal forms and the proofs for them. But sadly, for the sake of brevity, I can't go into that right now. As for an example, if we consider the XOR between A and B, we notice that the right AND term is negated. Luckily, however, we can transform this in such a way that we only have the input variables negated. So ultimately, as long as we have the negated values of the input variables, we can compute anything we want. And since we don't want to add extra logic to the memories, the authors proposed letting the CPU pre-compute this. Now, all of this only tells us that we can indeed compute anything we want to. However, with our current setup, we would still have to transform any formula before we can compute it. And depending on how complex the formula is, we might not want to do this. Again, though, there is an easy way to solve this. Let's, for example, assume that we want to compute the following formula and we, for some reason, want to do it without transforming it. If we were doing this on the CPU, we would first compute the OR between A and B, store it in a temporary variable, and then use that to solve the XOR. If we want to do that in memory, however, we would need the inverse of C to compute the XOR as well. Luckily, though, in the same way that we could have transformed the entire formula, we can also just transform parts of the formula, or in this case, the OR, and get the inverse of C. As long as we always have the inverse of any value, intermediate or input, available, we can compute anything we want to. This leads us to the framework the authors have proposed. We represent every value as a tuple of the non-inverted and inverted value, and let every computation compute both its non-inverted as well as its inverted result. This way we can compose operations as much as we would like to. The authors have performed this transformation for most of the important basic operations, which is shown here. For the sake of brevity, though, I will not go into more details about this. The important part is that we can perform arbitrary computations without needing negation logic available in memory as an operation. To finish up this part, I will quickly summarize some of the constraints of this solution. Firstly, the CPU will have to compute the inverse of all used values at the beginning. Then, since we are effectively storing each value twice, memory usage will be doubled. This is actually a much more serious issue than it might initially seem, and I will get back to this problem later. As seen, extra cycles are needed since every computation also needs to compute its inverse. And if we are using the elementary operations that the authors have provided, this will result in effectively a doubling of required operations. However, if we transform more complex logical formulas, we can improve this. The last mechanism we have to take a look at is bit serial versus bit parallel arithmetic. Typically, data will be laid out in the rows of the subarray. So for example, we could have some value A and some value B stored like this in memory. And we can have the same data, or we have more data in the remaining columns. This is how the CPU expects data to be stored. Now, let's assume we want to compute A and B. As we have seen previously, we first need a constant 0, and then we can activate the rows in the right order, and we get the results stored in all of the 3 rows. What we note is that the operation was performed on all bits of the value in parallel, hence bit parallel arithmetic. This effectively means that we can compute the AND or OR of up to 8 kilobytes of data in one operation. It is also advantageous since the CPU can easily or directly access that data without having to transform it. However, there is also a major issue with this approach, and that is that it is impossible to perform bit shifting operations since different bits are stored in different columns and we cannot copy data between columns. This is a very big issue as many more complex operations, for example, addition, require data to be passed between bits. And this is where bit serial arithmetic comes into play. In bit serial arithmetic, the data is stored inside the columns and not the rows. So for example, our value A could be stored here and B here, and again, we can have more data stored in the other columns. This time, we won't be able to perform the operation in place, so we need some rows reserved for the computations, as well as sources for the constants. Now, if we want to compute the result of the AND again, we first need to copy the first bit of the operand A, the constant 0 row, and the first bit of operand B to the computation rows. We can then compute the AND and store the result somewhere in memory. This now needs to be performed on each bit sequentially. And ultimately, we end up computing the AND for each bit. This allows us very fine-grained control over how operations are performed. For example, if we wanted to, we could only compute the AND of bit 1 and let's say bit 6 of operand B, or any other combination, really. It also solves the issue of being unable to shift data between bits, as all bits are stored in the same column. It is also important to note that we aren't actually reducing the maximum overall throughput of our computations here. We are still computing the operations on 8 kilobytes of data in parallel. However, the latency of any computation is significantly increased. A much bigger issue is that the transformation of the data is needed if we want to use it on the CPU again, as the CPU expects the data to be placed inside the rows. If we do not have special hardware, this can be very expensive, as we would effectively have to mask and shift to reconstruct the data bit by bit. And lastly, we are now limited by the number of rows for storage, which is typically significantly lower than the number of columns. To finish up, let's quickly review some of the constraints that arise from the proposed mechanisms. Operands are overwritten by any operation we perform, which means that we need to copy the source data if we want to use the data again. Then, next up, in order to be able to open up 3 rows at the same time, the operands and the constant rows each need to be in a specific location relative to each other. That does limit us in some ways, but also not so much in others. Then, since bit serial arithmetic always computes 8 kilobytes of data in one go, but can only work on 1 bit of a single value at a time, we require extensive data level parallelism to achieve high efficiency and throughput. Another issue is that all computations need to be in the same subarray. If we want to copy data across subarrays, we would have to perform an expensive copy through the memory controller and bus, which is what we were trying to eliminate in the first place. Lastly, if we want to perform arbitrary operations, a lot of extra memory is required. We need the reserved row for the computations, the constant 0 and 1 rows, as well as double storage for values. It is now also apparent why this double storage can actually be a serious issue. Since we cannot copy data across subarrays, we are limited by the number of rows. If we assume 512 rows and remove the rows for the computations, constants, and half the remainder, we end up with just 253 bits available for all data needed in the computation. And this includes any intermediate values and results. We can now look at how these ideas actually perform in reality. The authors used a custom system with a host, where a host system is connected to the memory by using an FPGA as a custom memory controller, running a modified version of SoftMC, which is an open source memory controller. Due to limitations of SoftMC, the data bus was limited to 800 megahertz, which is well below the typical maximum typical operating frequency of DDR3, which is around 1600 megahertz. Since the bus is running at a fixed frequencies, all timings in the results will be quantized to multiples of 2.5 nanoseconds. And to eliminate latency on the PCIe bus, all instructions were buffered on the FPGA. The authors then evaluated 32 different DDR3 modules from 7 different vendors, with reliability and feasibility being their primary testing goal. As a quick reminder, we are varying 2 timings here. First, T1, which is the delay between the first activate and the precharge, violating the row access strobe, and secondly, T2, which is the delay between the precharge and the second activate, violating the row precharge constraint. Also, all timings will be displayed as the number of idle clock cycles in between the instructions. This means, for example, that a 0 does not mean that there is 0 delay between the commands, but that there is no idle cycle in between them, or in other words, that they are sent in consecutive cycles. 1 cycle here is equivalent to 2.5 nanoseconds. Here we can see the results for 3 of the modules. Since 2 modules behaved identically, they share the right illustration. The colored squares indicate the results from using the timings T1 and T2. White squares means no meaningful change. The blue colors are the results from row copy, and the green colors are the results from logical operations. To start with, we can see the expected pattern for row copy in the right image. We reduce T2 to interrupt the drivings of the bit lines, but T1 should have less of an effect on the operation. However, some modules display the pattern seen in the left image. The authors theorized that for these modules, the sum of T1 and T2 is what determines success. However, since DRAM manufacturers don't disclose much about the inner workings of their modules, it is hard to tell for certain what is going on here. As for the logical operations, we can see that they require the timings to be as tight as they can possibly be with our 2.5 nanosecond clock cycle. And it might be possible to achieve higher reliability or operations on more modules if we were able to reduce the timings further. However, the authors have left that for future works. Here is a quick overview over all the results. We can see that all modules generally follow the same pattern as the previous two modules, and that especially on the modules rated for higher frequency, operations happen at the very edge of what is possible with our timings. Since the paper's primary concern was showing that it was possible, these results are very encouraging, even if there are only two modules, or actually in this case it's four modules with a 100% reliability on some operations. Speaking of reliability, here are the charts detailing the column success ratio for the operations. These are cumulative distribution functions. First, let's look at row copy. We can see that the worst module still had over a 53%, still had over 53% of rows with a 100% success rate. Another feature we would like is a fast success rate drop, as this would make it easier to potentially detect functional rows. In this regard, the highest degree of variation can be seen here, with around 18% of columns having neither a 100% nor 0% success ratio. And the NOR operations were much more reliable, with almost all rows having a 100% success rate. Well, obviously only for those rows that actually did show successful AND and OR. In terms of performance, here are the number of cycles needed for each operations if it is applied to one bit. Since this is using bit serial approach, we will need high data level parallelism to maximize our throughput. Now, assuming that we filled all columns with usable data, then row copy will have a peak bandwidth of 182 gigabytes per second, 8-bit AND and OR has a peak throughput of 19 giga operations per second, and 8-bit addition has a peak throughput of 2.46 giga operations per second. Lastly, energy efficiency. The authors modeled the energy uses of the DRAM using Vampire, which is an open source model. It is important to note that the energy cost model assumes that all DRAM commands finish execution, and this is obviously not the case in here, since we intentionally interrupt those. As such, the energy estimates are likely higher than what the actual energy consumption is. Ultimately, row copy is 347 times more energy efficient than copying the data to the CPU and back. 8-bit AND and OR is 48 times more energy efficient than performing the same operation on a vector unit, and 9.3 times in the case of 8-bit addition. To summarize, we have this major performance and power consumption bottleneck in computing systems, which is the interconnect between the main memory and the CPU. So we would like to alleviate this problem by performing the computations in memory. The paper proposes to violate the DRAM timing constraints to achieve a non-standard state, which would then perform these operations. Feasibility and reliability were evaluated on 32 different modules from 7 different vendors, and any module that was able to perform the operations was further tested for the performance of 8-bit AND OR and 8-bit addition. And as we have seen, nearly all chips were able to perform row copy on at least some rows, with 3 modules being able to perform the AND and OR operations, and the reliability of those operations was very high. Now for the analysis part. The paper achieves what it sets out to do, which would be demonstrating that it is possible to perform arbitrary operations in memory without any modifications to it. I especially like the creative approach that they use to solve the negation issue. And the performance and efficiency of the operations are also impressive. It is especially impressive when we consider that the area of a single subarray is 0.031 millimeters squared. So if we compare that to the size of CPU dice, that is very impressive. The solution is also very flexible, as we can use the memory both for computation and storage. So if, for example, want to switch, we don't need as much computation, we can switch some subarrays back to being used for storage. This is an advantage that other methods like adding cores, like adding special purpose cores to memory, do not have. Furthermore, many of the inefficiencies of using the proposed solutions can actually be optimized. And at the end of the day, if nothing else, then this paper illustrated that the mechanisms presented by row clone and ambit are indeed feasible. And I think that is already a great success. But all solutions also have issues, and this paper is certainly no exception to that. As I've already explained, only inter-subarray computations are efficient, which can be a serious bottleneck. Further, while the DRAM itself doesn't need to change, the entire rest of the system does, from the memory controller all the way up to application software. Also, the fact that this is essentially a SIMD machine, and we need close to 64,000 data points for efficient operation, it also raises the question: what are we going to do before and after a batch of operations? For example, we first have to copy the data to the CPU, negate it, then transform it, copy twice the amount of data back to the memory. Then during the operations part, the memory bus will at least be partially occupied with sending the instructions. And even after all that is done, we still need to copy the data back to the CPU again, retransform it again so that it can be before we can finally use the results. In this case, we copied the data effectively 4 times over the memory bus. So it is not obvious if we actually achieved our goal of reducing the data movement across the bus. Then there is also the need for all the negated values to be available, costing us valuable rows and requiring pre-computation. To finish this part up, one last point is that the paper was sadly also unfortunately worded in places, making it sound like they were the inventors of the chart sharing mechanisms, which were actually presented by row clone and ambit. Now, what they did do was show that these operations can be implemented without any change and how to do them without any changes. Also, now some quick personal ideas on how this could be implemented or improved. One idea I had was to enable the inter-subarray copy, because as we have seen, the negation framework incurs a high memory cost, which is limited by the number of rows available. And as such, if we could copy data between subarrays, that would significantly reduce the impact of this. There is actually a paper called Low-Cost Interlinked Subarrays, or LISA, that looked at how this could be implemented. The second point, the bit serial approach makes it impossible to directly interpret the data on the CPU. And while doing this transformation in software can be very expensive if you don't have special purpose functions, it is very cheap to do in hardware, as all you have to do is rewire some bits. So let the memory controller handle this translation. My last idea is about something I actually haven't talked about yet, and that is cache coherency, which is an issue pretty much all of these in-memory compute proposals have to deal with. In this case, though, I think there is a comparatively easy solution. Simply remove the subarrays that are used for computation from the addressable memory pool. This eliminates all cache coherency issues, as the row will never be mapped into cache anyways. It also doesn't cost us that much. Since the CPU can't directly access the data, the bit serial data anyways, we will always have to do some intermediate transformation before it can be used by the CPU. If we were really fancy, we could even make this a dynamic process. However, there are some new issues that would appear there. For example, alignment of memory pages, and significant changes to system software would be needed to accommodate that. Now we are finally done and we can get to the fun part. Before we begin with the fun part though, are there any questions? I'm going to look at chat, which I have on my laptop down here, so don't be distressed by this. Are there any extra, are the extra rows for row remapping like spare tires for DRAM? Okay, I like that comment. I'm not sure if you can I'm not sure if you can say like that, because you can always just replace more tires, but in DRAM, yes, you just have DRAM manufacturers. What you typically have is you have one sub. Can you see me? I hope you can see me. What you typically have is one subarray, and then the manufacturers would add 1 or 2 additional rows at the bottom of the subarray or somewhere inside the subarrays, and the DRAM and any faulty rows inside that subarray can then be remapped to use those spare rows. So in a sense, I guess. Are there any other questions? All right, since that doesn't seem to be the case, we can move on to the fun part, which is the discussion. Now, the first point is, oh yeah, before I get started, actually, it's important to note I'm going point by point through these discussion points, but honestly, if you have anything to say or want to discuss, feel free to say it about this paper. Like, these are just discussion starters, and if there's any good idea, we can we should be talking about it. So the first point is it worth adding the special purpose negation logic to DRAM over the presented framework? As I've quickly mentioned, the Ambit paper proposed adding logic to DRAM to perform these operations. It would actually be relatively cheap. They would add 1 row of transistors to one row, and that would then perform those negations. However, that is still a cost. So the question is it worth taking the costs from the presented framework, or should we take the costs from adding special purpose logic?
I have like kind of a question. So like you said, they add an extra row. So what if if it's a bad row, so it's not suitable to perform these computations? Isn't this like kind of a waste of transistors in the module?
That is actually a good point, and I did not think about it because that is part of Ambit. Yeah, that might actually become a problem now that I think about it. Yeah, that is a very valid point, and I'm sad because I can't really say anything about it since I haven't read too much into Ambit. But yeah, good point. Well, since there doesn't seem to be any other comments on this, we can move on. Now, this, as I've already stated, this requires extensive changes throughout the software stack. But there are also some more specific problems, like we could potentially make existing libraries like OpenCL support this, or can we not? There are a lot of questions here that we can answer. We can also think about it if we consider the fact that basically system integrators, and we also need support from like system software. So there is a lot of change that would need to happen, and we can also ask ourselves if it is worth it to do this change, if there's some ideas on that. Well, I guess there doesn't seem to be too many ideas here. Anyway, I mean, I have more questions. We can move on. That is not really an issue. This point right here is actually a pretty interesting point because we are using bit serial approaches here, which means we need high data level parallelism, which could potentially reduce this the applicability of this mechanism. So we can ask ourselves, how many tasks can actually use this mechanism properly?
I think it's like it could be useful in big data centers because they can utilize parallelism very well. And like you said, I don't have the numbers. Wait. So it's like 347 times more energy efficient than using a vector unit for row copy, for example. So like these big data centers, they're like a big problem for the environment if you look at the energy they consume. So like trying to make them more environment friendly is like probably a good idea, I guess.
Oh yeah, I really like that idea actually. That would make a lot of sense. And big data centers also have tons of memory, like we're talking terabytes of RAM per CPU. So they have a lot of potential parallelism that they could exploit by doing this. So I think that is a great suggestion actually. Anyone else who wants to comment on this?
Well, if we like adding on what was just said, I mean, generally any application that really uses a lot of copying of data and a lot of maybe even and or operations, which are possible with this approach, all of those applications could be really supported by this, because as you said, it has really a substantial decrease in energy used.
Yes, that is very true. So yeah, that's actually that can be a tons of different applications. I do like that.
I mean, we would just have to make sure that kind of we distinguish between the applications, or maybe even if we have really specialized hardware that has DRAM in it and does a lot of copying, like data centers. That was maybe one example of it. Yeah, those would be really well versed with this approach.
That is now a very interesting point though, because you're saying specialized hardware. So you're proposing taking DRAM modules and putting them in special hardware outside of system memory. Am I understanding that right?
Not exactly. Maybe more thinking about it like if we have some hardware which also utilizes DRAM and does a lot of those operations, then maybe this could be kind of a supplemental implementation. That's more the idea. It's like using what is already there but repurposing it in that sense.
Yeah, that is a perfect point, and that is also what the authors originally set out to do. So yeah, that is on point. That is perfect. All right, since there doesn't seem to be anything more about this topic, this is a more complex issue, and also it is a depressing issue to think about, but also a really interesting one, because as I've said, like with the bit serial and bit parallel approach, many of the operations that require this high data level parallelisms already have special purpose accelerators. And if software already has support for these special purpose accelerators, how valuable is it for the, or how easy, all right, it's like, what would a software developer what would make a software developer think, yes, it is worth it putting in the extra effort to support this new thing over my, or in addition to my special purpose accelerators? I will let some time pass for this question, because I do think that there's a lot of thinking that needs to be done to get, or at least that could be. So yeah, I will let some time pass here.
Well, I think I guess it would be worth for some developers, but only for developers that already care about the high performance and low energy consumption. So it would be, I think, a rather smaller subset of all current application developers, because we would only implement this acceleration methods if you already have a method that is highly system critical and that needs to be fast. So maybe programs that are already programmed in C or even assembly that would benefit the most of this method.
Yeah, that is probably a good point.
I think like it could be useful for machine intelligence, but like they have those specialized accelerators there. So, but like for example, it's hard to put a good one into a phone. Let's say it's easier to put it in a Tesla than into a phone. So maybe like you could use it for those things like Face ID, fingerprints. You could probably use it there and make those things a bit more efficient, just like for quality of life. But like
that
yeah,
yes.
is it? Yeah, I guess quality of life is worth it in the end if you want to sell your product, make it smoother.
I mean, yeah, most of these big software companies invest tons of money for the best quality of life features. But yes, that is actually a very, very good point. Because if you look at most current systems, even consumer systems, like Apple is putting a their neural, what they call their neural engine into pretty much every device they sell. So yes, that is certainly something that could be of high value for end consumers.
Also, maybe a question here to ask specifically for the wording of this question is what exactly are the specialized accelerators that we are talking about? Because sometimes maybe there are specialized accelerators which specialize in something else than what this approach is good for. So maybe this could actually also really help with speeding up optimization, specific instructions which aren't supported by the specialized accelerators, and then you would still do the other accelerated parts on those accelerators.
Okay, that is one thing I did not think about it, and I absolutely love this point. Like this is great. Yeah, because yes, we can have yeah, I love this, but actually great point. I love it. Yes, absolutely correct. I think that is absolutely true. No, being able to complement any complex system just by having Instagram, like, even just from the perspective of having for example, all the special purpose accelerators taking up all the PCIe slots in a big data center, and then just being able to use your RAM for others. Yeah, that is great. That's a great point. All right. I guess we will move on to the next point then, which might be which is the last point actually. And this is another interesting question is, since we are using bit serial approach, we have a ton of control over which operations we apply to which bit. Are there any interesting optimizations that we could theoretically achieve by doing it in this way? Yeah, so doesn't sound like there is much. I can let the minute run out, or otherwise I don't have anything else to say. Maybe if there are some questions left or anything to say, that would be a good point time to say it.
So Lorenzo, thanks for the presentation. Maybe I'll ask you your question. What do you think of the answer to your question, this last one that's on the screen? What optimizations could be enabled by performing operations in a bit serial manner?
I actually think there are a lot of optimizations. I also thought about, like, for example, when we look at how add is currently performed in CPUs, like we have this very complex tree-based add systems, but they all rely on high parallelism. And I guess in this case, it could be possible that we could optimize this in some way where, because we have like direct control to each bit and we can precisely perform each addition in it, we could potentially increase the overall throughput significantly. Compared to if you're doing it on a vector unit. Because, for example, in a vector unit, if we want bit precise control, what we would do is we would mask the data, then perform the operation on the data, then perform the operation on the data, then mask out the bits that we wanted to, and then combine that with the other bits again. So we could and in this case, any bit that was masked away was just wasted throughput. And in this case, we can use that throughput.
Yeah, that makes sense. I think certainly bit serial processing inside the memory has a lot of potential for very high throughput. It also enables you to do to perform, let's say, additions at different granularities more easily, right? You can do 2-bit adds, 1-bit add, 4-bit add, 32-bit add. You just use as many bits as necessary, as opposed to building a very large adder that can accommodate all of them. So yeah, I think what you said makes a lot of sense for sure. In fact, it becomes a much more efficient, I think, when you go to smaller bit widths, which is really the trend in some neural networks, for example, if you want to take that as an application. And if you do the calculation, it could be enormous throughput, right? Like, let's say you have an 8 kilobyte row and 1,000 subarrays, that's 8 million adds at the same time. Yeah, it's a bit harder to do. Yeah, and that's in a single DRAM chip, right? If you can do it across 1,000 subarrays, of course, it's a bit harder to do that in a CPU. Of course, you add more adders, yes, but I think the flexibility of doing different bit widths with bit serial computation is certainly enticing. It's a bit harder to achieve in logic. Of course, you could have bit serial adders in logic as well, but that's not what the trend has been so far.
Yes.
Okay, cool. Okay, I mean, I don't have any other questions, but maybe I'll add a few more comments on these papers. Thanks for the presentations. I think they were quite interesting. And it's good that you're asking questions to actually try to engage people. I know it's always hard to engage in Zoom, unfortunately. I guess let's try to engage more in future meetings too. These two papers are actually quite, they're selected certainly. Certainly people were interested in presenting them, but we put them together because they're two very good examples of new proof of concepts as to what you can do with DRAM without modifying existing DRAM chips. So the first one is a proof of concept that shows that you can generate two random numbers just by modifications to the memory controller, and if you want system stack also. And the second one shows that you could essentially do computation and copying, bitwise computation and copying of rows, again, just with modifications to the memory controller. So they're actually extremely promising. And I think it's good to think about what else you can do with DRAM without changing it. We call it processing using DRAM. Essentially, you're using memory for some other purpose, like random number generation or copying or bitwise operations. Maybe there are other things you can do also in memory, right? And DRAM is one example. There could be other memory technologies where this could be useful. And I think, as mentioned, these are not the first papers in this direction, right? Row clone and Ambit are examples of processing using DRAM, but clearly they required some modifications to the DRAM chips. And I think in the end, you may need modifications to the DRAM chips to be really reliable, right? As you can see from the ComputeDRAM paper, reliability is not perfect. You can only do these operations in some rows. In fact, when you get to AND and OR, it becomes even smaller. And for NOT, I think Lorenzo mentioned that he liked the immersion solution. I don't like the immersion solution actually because it's not very intuitive. But I mean, there's nothing else to do, of course, right? Because you cannot just do inversion or complement with the existing primitives that you have inside the DRAM memory. So I think Ambit, in a sense, so I see this work, ComputeDRAM, as a proof of concept that shows that the concepts of triple row activation and back-to-back activation introduced by Ambit and row clone are actually viable in existing chips. So from that perspective, it's very valuable proof of concept. But I think in the end, if you really want to implement these, I don't think not changing the DRAM chips is a good idea, because you want things to be reliable and predictable as well. You don't want to be basically exposing something where the programmer can do these operations only in some part of the memory, for example, or in particular rows. But I think these proof of concepts are extremely important also. The key, I think, after this point is how do you actually get to enable the ideas that these proof of concepts demonstrate? And that was part of the DRANGE discussion, for example. What does it take to enable DRANGE in real systems? And that requires more work, of course, in terms of implementation in the system stack. But I would encourage people to think about what else can you do, because the thinking so far has been memory devices are memory devices. You just store data in them and get back data. But clearly, these devices are much more capable than how we have restricted ourselves in treating them so far. And I think there might be other ways memory can serve or be useful for us. Maybe I'll end with that comment overall, because I think that's a good opportunity for future research, thinking, and brainstorming. Okay, if there are no questions, I think we can probably call it a day for today.
I've written a question in the chat, whether this DRAM compute can be used for Bitcoin mining, since it is known that mining Bitcoin costs more energy than it produces on average.
Mm-hmm. Yeah, so that's a good question. Basically, I think whether okay, this I think brings me to maybe pointing at some prior work. So I think that requires an analysis of where energy is spent and performance is spent on Bitcoin mining. I don't think we have analyzed that application, but I think it's good to do an analysis of where you're spending energy. If it's spent on data movements, then certainly, yes, not moving data outside of DRAM can buy you a lot of energy reduction. And I think that could be very powerful, certainly, assuming, yeah. And then also it depends on what kind of operations are you doing to mine Bitcoins, for example. So I think that analysis needs to be done for many applications. And I'd recommend looking into the application. If you're excited about this, for example, certainly you can analyze, break down where the energy is spent, or where the performance also gets spent in an application, let's say like Bitcoin mining. And then you can simulate how much benefit you can get by in-DRAM computation in the style of, let's say, ComputeDRAM or Ambit, or near data processing as well, right? So in general, if data movement dominates your energy in an application, that's where you can gain a lot of benefit. I will also, maybe I'll share my screen quickly, mention that there's more work in this area that's coming, and Geraldo didn't mention it maybe, but you can see my screen probably, right?
Yes.
Can you? Okay, good. Yeah, I'm showing, this is my page publication. So we have one paper coming up. Geraldo is a first author, co-first author with Nastran. That's called SIMDRAM. You can imagine what SIMD stands for, right? Single instruction, multiple data, DRAM. And this is an end-to-end framework for bit serial computation in DRAM. And I'd recommend looking into it, because what this work does is, we don't have the full paper available at this point yet. It will be soon. But what this work does is it's basically provides different primitive operations like addition, multiplication, etc., using just bitwise majority and not inverter operations, and provides an end-to-end framework where you can convert these operations, where you can convert, where you can actually call these operations from an application, for example. And I think there's more work to be done in this area as well, as we might discuss later. Geraldo, do you have anything to add here?
I think the only part that I would add is that the nice thing about this paper, I would say, is that we provide a way of implementing theoretically any computation that the user wants. which brings a lot of flexibility, even for like, I was just Googling here, if I could see a benchmark suite for Bitcoin, because now I was curious now to see what are the primitives that are being executed there. But for example, if there is a operation that you want to accelerate in DRAM computing now, using our framework, you can easily do it. So we don't implement it in hardware as ComputeDRAM for the moment. We do simulation, but since ComputeDRAM provide like this gap, the ComputeDRAM provides this gap between the simulation and the hardware. Likely that could also be implemented in a real system.
Yeah.
So yeah, so
I like to just add something, the fact that providing this ability of flexibly supporting any desired computation operation using DRAM, our framework is the first one, as far as we know, that enables such capability. So
yeah, maybe in the next semester, this paper will be part of the seminar paper list, and I think it could be a good thing that essentially makes the ComputeDRAM and Mbit and row clone mechanisms much more general, much more flexible, and hopefully much more impactful going into the future, because it enables applications to arbitrarily use them. Of course, when these operations would be useful to do inside DRAM. Okay, I think this is a good place to stop. Anything else? Juan, do you have anything else since you started?
No, I don't have anything else. Just to let everyone know that we are going to activate the questionnaire as usual, and it will be available soon. Thank you very much, everyone, and thank you very much to the presenters. See you in our next session.